Can you see my screen? No, not yet. Wait. Now? Can you see my screen now?
Yes, sir.
Yes, okay. Okay, so let's get back to where we were just before the exam. We started talking about network layer, whose primary functions, as we have seen earlier, is routing and something called fragmentation that we'll see. Routing, we have already seen what routing means. So this notion of both building the routing table as well as forwarding the packets using the routing table onto their path to the destination. And the predominant protocol that we're going to study in network layer is IP, and specifically IP version 4. This is the standard IP that is being used. I will not say most commonly, but yeah, that's what you know. So we have gone through these basic things, what is an IP address and so on. Okay. So this is the thing, other thing that, oops, sorry. I just want you to remind basically that even though we say an IP address for a host, machine, etc. routinely, an IP address is actually assigned to what is called a network interface card. So these are kind of terminologies came from old days where everything was a separate card. Nowadays, many things are just inside the motherboard itself. Okay, but it's basically actually assigned to what is called a network interface, the actual thing through which you connect a wire or wireless thing and so on. So machine may have more than one IP address, it has more than one. So in a standard laptop, if you connect to both a LAN cord and a wireless and you enable both of them, then this is a standard example of something with two network interfaces. But again, I want to point out the term host, machine, device, these are all going to be used interchangeably. So we'll routinely say an IP address for a host, machine, IP address for a device and so on. But that is what it means. We looked at class A, class B, class C, class D. Okay, you don't really need to remember these ranges or these high order bits or something. Okay, nothing to be remembering this about. But just remember that class A basically means that you have is the largest network that you can have. You have 24 host bits, 16 for class B and 8 for this. So with this, the maximum number of IP addresses you get is 256. This is 65, 536. And this is 2 to the power 24 minus 1. So, and this other important thing, just to recollect that we said that we specify a network. Okay. So when I say class A, if I say this is this and this is the class A, and you look at the higher order bits and all, you automatically know that only top 8 bits are network, the remaining 24 bits are host addresses. So in the old days, there were only these three rigid divisions, 8, 16, 24. These are the only possible parts of the, or possible types of the network part that you could have had. And given an address, you could have used this top order bit, top 2 bits, top 3 bits to identify whether it's a class A, class B and class C, and therefore you know how many network bits and so on. So in the old days, you needed only the IP address. If I give you basically 144.20.30.40, you will look at the top 1 bit. If it is 0, then it's a class A. Otherwise, top 2 bits, 10, it's class B. Otherwise, top 3 bits, 110, it's a class C. And then looking at these bits, you can say, okay, class C, therefore, up to 24 bits is the network address. I have only these things to manipulate. Okay, so you needed nothing else other than looking at the IP address to distinguish, to find out what the network part is. However, as we have shown earlier also last class, that now we go for what is classless, because classful is a wastage. If you need addresses for only 30 machines, you're an organization, okay, you still have to get a class C. So 200 plus addresses gets wasted. If you need 500, it's even worse basically. Fine, you get 2 class C's basically. Okay? Not too bad. But then if I need 20,000, I get a class B. That means more than 45,000 addresses are getting wasted. And since it's a fixed quantity, and since number of machines that are connected to the internet was increasing rapidly, It was felt long ago in the 90s itself that classful addressing, that's allocating a class A, class B, class C is bad. Which means my network part can be variable, can be anything now. So how do I specify, given an IP address, which part is the network part, which part is the host part? So there are two ways. One of them is a very standard way, is to show slash this saying that this many bits from the beginning are the network part in the 32 bits. The remaining parts are the host part that the organization can assign addresses with, basically. Okay. So for class A, I will write actually, I will not look at the top bits or anything anymore. I will say /8, so top 8 bits are network and 24 bits are host. /16 for class B. But then I can do anything. This can be anything. So anything from 1 to 32 basically. Okay. 32 doesn't make sense because then they have nothing to address basically. But we'll see that it is also a possibility in some cases. Okay. So given that I have a host, I have an IP address which actually logically is a network part and a host part. Here are just some special addresses that IP addresses that look at basically. So one of them you have already seen, this 127.0.0.1. It's what is called the loopback address. It allows applications on the same host to communicate using TCP/IP. If I don't want to go outside my host, only within my host to communicate, I can use this as the machine, the network interface. This basically says this machine, this local machine base. However, suppose this is my network part, this is my host part. Okay. So this has some bits, I do not know. If I put all ones out there in the host part, okay, which is basically says similar to MAC address, I put all ones in the entire 48 bits to say broadcast to all machines in the LAN. This says broadcast to all machines in this network. That means all other machines that may have 0001, 100, blah, blah, blah. Okay. So it's called a net directed broadcast to this particular net directed because it's broadcast only to this network. Okay. So this address, just to remember then, that means even though I'm able to manipulate this host part to assign addresses to my machine, no machine will have an address where the host ID is all ones. Because that's a special reserved thing to indicate something special. Basically it says if I send out an IP packet with a destination IP network with whatever network, host with all ones, it's interpreted specially as saying everybody should process it. It's a broadcast. Similarly, if it is all zero, this is not assigned to anybody. This kind of a more a representation of the network. How do I say this network? Okay. So this network, I'll put the network, whatever the network bits, and then just all zeros in this thing. So this is again not assigned to any host, basically. Okay. So out of all these things, basically, so any network, if the network has a total of k addresses, okay, the number that you have for actually assigning to hosts is k minus 2. All 0 is not assigned in the host part, all 1 is not assigned in the host part. Okay. And then there are certain blocks which are called private IP addresses. You all already seen private IP addresses in machines here in Kharagpur and so on. But these are the blocks 10.0.0.8, that means 8/8 means only this. This you can vary as you want. This one is actually not exactly 8 or 16 or something. So it's actually this range is a 20-bit block. So 20-bit network address if you work this out. And the 16-bit where you can have this basically. So we'll see its use, okay? But it should be used only internally in an organization, should never go on the internet. So we'll see a little bit more of what this means at the end. Okay, but so remember there's something called private IP address. So private IP and the remaining ones are public IPs basically. We've already done this problem with classful. That's a huge wastage, and you may run out of IP addresses. So you did classless. Okay. Now you stopped looking at those top bits 0, 0, 1, 1, 0, 0, etc., etc. You said, no, I'm not going to look at this thing, not try to find out from the IP address, looking at the bits, is it a class A, class B, and so on. Because now my network part can be broken up anywhere, not just at 8, 16, and 24. Okay. So just an example, I think this we have already done this, so I'll quickly do this. If you need 56 IP addresses, okay, you don't need a class. Okay, so classful would address give a whole class. that means you waste around 200 addresses. But with classless, what I will do is I'll break up these 256 addresses in a class C into 464 address blocks. Okay, so that means class C had these 8 bits. Okay, I will borrow, because I don't need to change all of them. I will borrow 2 more bits from this as the network part. So this is 6 bits remaining, 2 to the power 6 addresses. Okay, and that will give me my 64 addresses, out of which all zeros and all ones will mean something special. Okay, so I will do the allocation out of this network, out of this class C network, /26, because 24 plus these 2 out here. This 24 was from here basically. So that leaves me with the remaining 192 to be allocated to somebody else in the same map. Okay, or I can club 2 of those 64s again to give somebody 164, somebody 120, or I can give 3 of them 64s. I can break them up further to say 632 blocks. Okay, so this is what is called classless, because I no longer look at the stop bits or something, but I rely on something else that I did not have to specify earlier. So this one, and this is what is basically your subnet mask that you all set in your things and so on. So we'll talk about this very soon. This I will just ask you to read again. I've done this. So you allocate centrally. So there is an organization actually on top of even all this called ICANN. Okay, so ICANN through IANA manages this allocation. So it's not that you cannot use, because you want the IP address to be unique across the world. So far, we'll talk about private IP addresses later on. So what IANA does is it takes this entire chunk of block and gives kind of contiguous blocks to regional registries. So Afrinic is for Africa, APNIC is for Asia Pacific, LACNIC is for Latin America and Caribbean, and so on. Okay. And ISPs in those regions will apply to this regional RIRs in their region for getting IP blocks, and then ISPs will give to their customers as well. As I mentioned, you can also get directly from RIRs. For example, we as IIT Kharagpur has got some blocks. But again, there are policies that govern, because this is a precious resource basically. And we'll see why this hierarchical structure, how that helps very shortly. Okay, so this is what we have done so far. This notion of an IP address being broken up into a network part and a host part. Okay. This notion of classless addressing and how it's allocated. Okay, you only allocate what is needed. The next higher multiple of 2. Okay, you cannot allocate 2, a non-multiple of 2, of course. Okay. Now, given this, suppose IIT Kharagpur has got a block. Okay, some chunk of IP addresses. So a subnet. Okay, the subnetwork is a subdivision of a network, obviously. Okay. Now, similar to this binary tree. Okay, binary search tree, just recall your definition of binary search tree. Okay, so we use the term tree and subtree. Okay, left subtree, right subtree, but then a subtree has all the properties of a tree. The same thing holds here. I get a subnet by dividing a network, but a subnet is also a network on its own with all the standard things that we talk about a network also applies to a subnet. The subnet is also a network, and subnet is subnet even further, and so on and so forth. Okay. So I'll take an example shortly. So just quickly go through this. Breaks host part further into subnet part and host part. Why do we do this? Allows better network administration and management. So for example, IIT Kharagpur, what it will do is it got a chunk from its ISP or whatever chunk here, and then it can say, oh, CS will be one subnet, E will be one subnet. Okay. E and EC will be one subnet and so on. Okay. Now, CS may again break subnet this further, saying faculty is one subnet. Okay, maybe RS is another subnet, and so on and so forth. Okay. So the local management of the routing tables and all, the CS will do its own things, E will do its own thing, each will do own thing. Okay, this does not need to know what is happening underneath. Local security policies can be set and so on. So typically we subnet. So subnet is inside an organization. The subnet usually inside an organization. Okay, it allows better network administration and management. and it reduces the route table size. We'll see shortly what this means. Okay. But let's understand what is a subnet. So it's a network mask, subnet mask. Okay. So subnet mask, as you know, we have already 255 we specify things like this. Okay. So it is a contiguous ones followed by a series of contiguous zeros. And the ones portion identifies the network portion of the address. And the zeros portion identifies the host portion that you can. Okay. So we'll come back to this slide, look at an example. So suppose I have a class C network 194.16.100.0. So if we see something, this you will see in practice regularly, that we have got a classless address thing now. Okay, so we no longer look at the top bits and we rely on this subnet mask, that slash notation, which are basically the same thing, okay, to do subnetting, etc., etc. But we routinely use the word class C networks, and so on. Basically, because that's what we started. It's just that during allocation, one of them will be broken up into different subnets and so on. Okay. So I hope you understand the difference. Even this is critical to understand. Like old days, I never needed a subnet mask, because if I look at it, if you just give me an IP address, looking at the top bits, I can say it's A, B, or C. And moment I know it's A, B, or C, I know what the network part is, because there are only three possibilities: 8, 16, and 24. But now that the possibility is anything, okay, the prefix can be of any length. I don't have the top bit, so I have to specify in some other way in addition to the IP address, and that is what that slash notation or the subnet mask is, which are the same thing. The subnet mask specifies at 1111 this form, because that's what we use. We'll see how to do what. The corresponding slash notation, in this case, for example, 8, 8, 8, and 4. So that is 24 plus this. So we would have specified slash 28. Okay. So there's two ways of representing. So if I apply this mask, so 240 is basically 192 plus 128 plus 64 plus 32 plus 16. So that's why this 4. 240 is this thing, 11110000. So this means this is the network part, this is your host part. So you can have at most 16 addresses. Okay. Address of first host on this network will be .1, because I said even the first bit pattern is all 0. This is special. This just represents this network. Okay. So you cannot put any address. Last host will be 14. 1111 is special. Again, it's a broadcast within this address. If I specify 194.16.100.15, this will actually specify to all these ones, and then 1111, which means basically just broadcast to those maximum 14 machines on this network. The next subnet will start from 16 and will go on to how much? What will be the last? So this is the first address of the second subnet. Okay. What will be the last address of the second subnet? With the slash 28 mask? Anyone? Come on, can you hear me? First of all, can you hear me? Yes, no, please. Hello?
Yes, sir.
Yeah. So what would be the next subnet with the slash 28 mask? Basically, slash 28 basically says this is the one. Okay. So
yes.
What would be the next subnet? How many machines will it have?
16 square.
16 square.
No, I'm sorry. I didn't think it clearly.
We see if I do 16, go up to 31. Okay. We'll come back to this. I'll have a more detailed example later on. Okay. But here is how we use the subnet mask. Okay. And we'll just understand a little bit now. We'll do this more clearly. So if I give you two IP addresses, now these are IP addresses. Okay. and I say, are they same subnet or not? Now, when will they be same subnet? If their network bits are the same. Note that these are not their network address. This is basically saying that these are the bits that define the network address. That means top 28 bits will be your network address. So this is basically saying if this along with this subnet mask says top 28 bits of this address are the network address and the remaining is the host address. Okay. So now if you look at this thing, top 28 bits, 3 is what? 0, 0, 0, 0, 0, 0, 1, 1. Okay. And what is 12? 0, 0, 0, 0, 1, 1, 0, 0. Okay. And then you have 24 bits before this, 24 bits before this. So what I will do is I will bitwise AND this address with the subnet mask. So remember, subnet mask, these are all ones, the network part will come out. Okay. In this case, this all zeros will come out. Up to this will come out. And I will bitwise AND this address also with the subnet mask. So this will come out. I'll compare them. And if they're equal, I'll say these two IP addresses belong to the same subnet. Okay. So this two belongs to the same subnet because when I bitwise AND these addresses with the subnet mask, what I get is the same. So these parts will be zeros because they have ANDed with 0. These parts will be all 1. So the thing, whatever it is, will come out. So mask is not the network address. Masks are defining that these bits in the network address define the network part. That's why you have contiguous ones and the contiguous zeros. Okay. If I do the same thing with this now, so now 3 will 0, 0, 1, 1. What is 19? 19 would be 16, 0, 0, 1, 1. Right? So now if I bitwise AND this will come out to be 0, this will come out to be 1. So these two are in different subnets by the previous two. Are you with me? Yes, no?
Yes.
Everyone? This is very important to understand.
Yes, sir.
Okay. So subnet mask is nothing but another way to represent this. It's represented like this because this is, even if I say /28 or /24, /26, whatever, when I use it, I will use this bit pattern. I'll bitwise AND the two addresses, and if they're the same network, I'll say this is the same. Now, what do I do when they're in the same network and so on? That we'll see. But this is how I find out, given two addresses and the subnet mask, okay, whether these two are in the same network or not, as per that subnet mask. Okay. Now, given this, you understand A, B, and C are natural masks, basically. Okay. Class S mask is I can specify. Again, you will see, it's not that class A, class B, class C has disappeared. Okay. I'll also point out at the very end, basically, I don't want to spend time now. Not very end means very end of this IP lectures. Okay, I'll show you the allocation of class A, class B, and so when there were plentiful addresses. So effectively, a class C network, I can just specify an IP address and I can specify mask of 255.258.210.6. Can you hear me? Yes, no?
Yes, sir.
Yeah, it got cut for a second. Okay, no problem. Okay. So we know about IP address, by network, and so on. And this is the part that I want you to follow carefully. We'll go slow. We'll continue tomorrow. Okay. So we have seen this notion of a routing table. The routing table will be built by the routing protocol, right? And then we use that routing table for forwarding. So the next today's class, maybe at the beginning of next class also, is a question that we are trying to answer is, if an IP packet comes to an IP layer, okay, how is it forwarded? What happens to that packet? Okay? And I kind of want you to visualize this flow a little bit. So try to follow with me. Please talk with me. So first of all, I will use the routing table. We have already seen forwarding will use the routing table, but now we'll put some specifics in that. So already seen the typical fields. We have a destination field. We have a next hop field. We have a cost field. Okay, that's a typical fields in a routing table. And these routing table entries, IP routing tables, can be filled by a routing protocol running in the background, as we have seen. Distance vector, link state, we'll see there are different options. Or I can manually add routes also. Some routes will be added manually, static. These are called static routes because these are manually added. They won't change automatically if the network conditions change. So I have to manually change it again if I want. So it can be both static routes or dynamic routes populated by routing protocols. So this is a very, very high level flow. Any IP packet received from the Ethernet layer will be checked against the routing table. Okay. Okay, this is, I should cut this part. Okay. This should be both ways. Okay. So both, if it's received in the Ethernet layer, you will see whether it is for you. Otherwise, you will do something. Or if it is from the top TCP layer or UDP layer, you will see how to direct it basically. Okay. We'll see. Forward to higher layer if this machine is the destination. Okay. Forward to next hop using the interface in the end. Okay. So this is a typical, why I wrote the Ethernet layer is a typical router or destination machine. So for TCP to generate data and get to IP, that has to be source also. Okay. But then yes, so I will modify this slide a little bit. Your machine can also be the source, as we have in the next slide. Okay. But broadly, any IP packet received in the IP layer will be checked against the routing table, and I will decide where to forward it. Either it's for this machine, in which case I stop, otherwise I forward it to something. But to see how it is forwarded, I need to see what is in the IP header. Remember, every layer puts its own header because it will forward based on the fields in that header. So that is the purpose of the header. It will have some fields. Look at the header fields and say, oh, this is the thing, then I will do this thing, basically. So what are the fields in the IP header? Okay. You have a version which will be 4 for IPv4. For IPv6, it will be 6 and so on. Okay. You have a header length. Okay. So if you look at this is 20 bytes. So this is 32 bits, 5 of these blocks, 4 byte source address, 4 byte destination address. Okay. But then IP headers can be variable length because there is something called options. Okay. So this will basically be in 4 byte blocks or 8 byte blocks. Okay. What is the number? I think 4 byte blocks. Yeah, 4 byte blocks. Okay. So minimum value this can have is 5 because 5 into 4 is 20. So 20 bytes. Okay. Maximum will depend. It can be up to 60, though that is 5 into 12. Okay. But that will depend how many options you put. Okay. Then there is a field called type of service. Don't worry about it now. Then this will say total length, but this is only the header length. Oops, sorry. No, sorry. This is the total packet length. Okay. Yeah. So this is the total, header plus data length basically. These fields ignore for now. This relates with fragmentation. I will do them in detail when we come to this. You have a protocol field similar to Ethernet. So similar to Ethernet, which can carry IP packets, ARP packets, and so on. So when a packet is received at the Ethernet needs to know who to give it to. Same way, IP will need to know which is the higher layer protocol it can give it. Okay. Because TCP packets can be this, UDP packet. Similarly, when it sends it, it'll have to put that header field out there. So there'll be a code for TCP, there'll be a code for UDP, and that's what will be here. Okay. Now this time to live, or let me come back to this. Header checksum is just a checksum of just the header. So there is no checksum of the data. So that again brings you to this, interesting question that I asked you in the exam. So this means that in an IP packet, if the header is corrupted, the other end IP packet, IP layer will be able to detect it. But if the data is corrupted, it won't be able to detect it. So the natural question is that why don't we do a checksum over the entire thing? What do you think? Or we leave that question for later? Okay. Why don't we? You need to know something more to answer that. We don't do it because the same reason is met. It's costly, it takes time, and somebody else does it anyway. So we leave kind of IP is a best effort service anyway. IP does not guarantee any reliability. So IP is saying that what is the point in doing this much reliability when the packet can get lost anyway? Okay? So let somebody else worry about it, and we'll see what the somebody is later. The higher layer has to worry about it. And there is a field called time to live, which is typically called TTL. Okay, so we'll see, and this is some exercise that you should work out after we do the routing protocols somewhat more. That in a dynamic routing protocol, because things are changing, you can get routing loops temporarily at least. Okay, that means A will send to B, B will send to C, C will send to D, D will send back to A. Now, for some reason, whatever may the reason, if a packet does not get to its destination, okay, for a long enough time, maybe because it's looping, okay, maybe it has got on the wrong way and somehow some router was wrongly configured, it sent it on the wrong path, okay, then it should be taken out of the network. So time to live is basically what you put a value, typically 32 and all, because you assume that within 32 hops everything should be reached. So every router will decrement it by 1, and if it ever reaches 0, okay, then the packet will be dropped. So we'll come back and do this processing even more. But just remember this kind of thing basically. So version is just a value 4. Header length specifies the header in 32-bit words. Type of service. In the original days, there was a lot of things about, kind of specify, kind of try to distinguish between IP packets that minimize delay, maximize throughput. So routers will treat different IP packet differently and so on. Largely ignored. Did not pan out. It has some other redefinition now, but I will not go into that. But typically type of service field as is defined in the standard Ethernet IP header is not really used. So you just remember there is type of service field. There's a lot of experimental work, a lot of academic research on it, trying to use this for different things and so on. But practically, almost all routers ignore it. IP implementations don't use it. Okay. That's type of service. Datagram length is header plus data. These 3 flags, fragment option identification, forget about now. They deal with fragmentation, we'll do them in detail. Time to live is kind of, as I said, the upper limit on the number of hops a message can go before being done. For some reason, if this packet is kind of got lost in the net and was circulating, it should be eventually taken out. Okay. And we'll see what happens. Protocol, as I said, identifies the higher layer protocol whose data is being carried into this IP packet. Header checksum, only the checksum of the header. So again, you should keep this question in mind. Why don't I checksum the data? That would be more reliable, right? Okay. And then you have source address, destination address, and you have some options. I have given the options here. You don't need to remember, they're not in the exam. But remember, there are some options. That's the only thing I want you to remember. Okay. And this thing about specifying a length and then specify the variable size data is a very common technique in header. So it has variable length things that is important. And then there are some options in IP, very important. But again, not much used commonly. Very, special cases, 1 or 2 of them will be used. So you don't need to remember them and so for now. Okay, so given this header, back to packet forwarding. So first of all, I'll have 2 types of machines. If you think about this net, one will be like your desktop, laptops, your mobile phones and so on, which are sources and destinations of data, which will produce data, which will consume data. Okay. They will belong to some subnet, like my thing belongs to my desktop belongs to faculty subnet of IIT Kharagpur subnet and so on. So they can have only one NIC with an IP address assigned, or can have more, as I said, wired or wireless. But I can have something, a desktop with only the LAN connection, no wireless card. Okay. Typically, their routing tables will be static. By static does not mean I always have to type things, but then you typed your IP address network or DHCP gave it, okay, and that will be put in there. So there is no routing protocol, this distance vector link state that I am saying. Typically, they will not be running. It's not that they cannot, okay, but typically that's what will happen. And then each subnet will have a gateway that connects to the rest of the larger network. I'll draw a picture shortly. But let me just say what is, as opposed to this, what is the other? The other is the routers, okay, the switches and routers and so on. So their job is to route the packet, so not source or destination. So it connects more than one network. The other, unless it connects more than one network, there's no job of the routing. Okay. And this will require a picture, but just leave this thing, then we'll see. Connected to the gateway router of each network, so must have more than one. So you will not find a router with a single network interface card. Okay. And each NIC will have an IP address assigned from the network it's connected. Typically, we'll run some routing protocols, but as I said, I can also add static routes. This is larger size, more complex, more costly. We'll do them more, but let me kind of say what I mean. So this is, for example, suppose your desktop. Okay. And actually, sorry, let me draw this desktop a little large. And then let me have routers, and then this is another desktop. Okay, so this is a desktop, this is a desktop, this is a router, this is a router. Okay, so you see, think of this, just think of a pure wired network on for simplicity. Okay, so there'll be a port out here, this will connect to some port out here. Okay, then there'll be some port out here, the wire will connect to some port out here. Okay, there's some port out here, wire will connect to some port out here. Okay, so this will have an IP address. Okay, actually desktop will usually, so this is my gateway. Okay, sorry, and then let me have my desktop here. Okay, so let me have, this is the gateway, and let me have the gateway is also like a router. That's the term. So these terminologies can get very confusing very fast, but I just want you to kind of try to. Okay, so this will be in some subnet. This is in some subnet. Okay, so let's say this is an address 192.10.10.1. So this NIC will be connected to this NIC. This NIC will have the same address in the same subnet. So let's say 192.10.10.2. Okay. So this gateway has two network interface cards, with one card connecting to this network, let's say 192.10.10/0/24. Okay. Then with this and this another network. So this may be a network 200. So this is an IP 200.5.10.2 and then 200.5.10.5. So this is the NIC address assigned here, and this may be the network 200.5.10.0/22. Just suppose. Okay. Similarly, this may be another network. So 240.1.2.3 and 240.1.2.5, and this may be the network 240.1.2.0/20. And then this may be another network, 192, can be anything. Okay, and it's just random things that I'm putting out here. 60. Okay, whatever. I think this you can repeat this here. Okay, so these are your source and destinations of data. This will have only one. It can have only one. It can have more than one also. Okay, but can have only one link. Whereas a gateway, which is just another term for the subnets router, typically used. Okay, or a router, which is one of the more routers basically, but they're both of them function as routers. Okay, they must have more than one network because they connect networks. This gateway is connecting the network 192.10.10.0/24 with the network 200.5.10.0.20. So it must have one interface here to take the data from this network and one interface here to put the data on that network, or vice versa. Same with this router, it must have one interface here, one interface on the other network, at least. Now a router will typically connect to some other networks also. Okay, and these lines that I'm drawing are for now physical wires that are the cables that are going. It could be wireless links also. So is this clear what I say here? That must have more than one NIC. Each NIC has an IP address assigned from the network it is connected. So this NIC is connected to this network, so it has an IP address from this network. This NIC is connected to this network, so it has an IP address from this network. This network. Is this clear? Yes, no? Just kind of try to visualize physically, okay? Kind of, you know, you have wires going and these routers have ports. But then from each router, basically there has to be at least two network cards. If it connects more than two networks, then you'll have, for each network, it will have one network card. Is it clear?
Yes, sir.
Okay. And then processing wise, what will happen is, so let's say this is a sender. This is the IP layer. Okay. So sender will send data here. This will go through Ethernet. Then this go here. Out here, it will not go above IP. So gateway will check, am I the destination? Suppose it is sending all the way to here. So it's not. So the IP layer itself will use the routing table to forward this. Again, send this packet down Ethernet layer and it will go up here. And if IP is here, this will go up here again to the IP layer. It's not going up there until it's the destination. Again, here the routing table will be consulted. Okay. And find out what is the next stop. It could be any of these links. Suppose it is this one in this case. And go up to physical Ethernet again to the IP layer here. And then again this is processing. Then this will go to IP layer here. Now this will send to here. This will find out that the destination address is for me. So this will send it out to TCP or UDP, whatever. We'll look at the protocol field and figure out this. Are you with me? So this will first put all the fields. What each of them will do is to first, when it receives the packet, it'll first do the checksum. Okay, well, not necessarily first in that order. Okay, we'll do the checksum to see if the header is proper or not. If it is not, the packet is dropped. IP is a best effort service. If the checksum is fine, okay, then look at the TTL field. If the TTL is 0, drop again. If not, decrement the TTL by 1. Because it has gone through one hop. Remember, the TTL is kind of saying this is the maximum number of hops the packet is allowed to go through. So it has gone through one more hop, decremented by 1 before it goes out. Okay. Decrement the TTL by 1. Now take the destination address, see whether it's for this machine, then pass it up. Okay. If not, look at this forwarding rules. We'll do some more. Okay. And there's a lot of details out there again. And then pass it to the next stop. Find the next stop, do the next stop. You think about the routing table that you have studied so far. Just for a second, it's not like that. Think that each of those destination address is the IP address, and against that there is a next hop. If the next hop is this one, send it here, and then this will follow the same path. Okay. Well, the checksum TTL and destination is not necessarily in that order. Okay. TTL is typically what you set first, because if it is 0, you don't need to do anything. But you understand the process. Is it clear so far? Yes, no? अरे कोई तो कुछ बोलो यार.
Yes, sir. Yes.
Okay. So we'll not do this because we're running out of time. Tomorrow I request you to come, proper time, because tomorrow we need to cover a lot of things. We're going a little slow, but that's okay. It's very important to understand. Now you see, think of this router. This is going to get, connected, as you go higher. The CSS thing will connect to only the computer center's router. Computer center's router connected to BSNL, let's say, Railtel in our case. Now Railtel has given this ISP, has given connection to many other people. So their all routers will also connect to Railtel. Okay, so it will get a lot more packets. Okay, and a lot more packets will come through it. IIT Kharagpur's packet will come through it, maybe IIT Bombay's, maybe whoever has taken ISP. So now to do what I just said, I have to look up the routing table, look at the destination address, and find out what is the next one. Right? So which means, think about the Railtel's router, which means for every destination, that means all IP addresses that are actually assigned in all the organizations that it has given connection to. Okay, it must have one entry. You agree? Just give me a couple of minutes, but think with me here. Think about that, Kharagpur, CSE, Computer Center, Railtel. And Railtel's router is connecting like 100 different organizations' routers are connecting to Railtel. So when a packet comes to Railtel, and Railtel has to look at the destination address and say, oh, this has to go to IIT Kharagpur, or say this has to go to IIT Bombay. Okay. It must have an entry saying destination address, the current address, IP address. Next stop is IIT Kharagpur's router. Which means for every address that IIT Kharagpur connects to, or some other organization connects to, there must be one entry in the router of Railtel. Do you agree? I'm really looking forward to the offline class. I have no clue what is sinking in or not. Do you agree or not? Let's leave it to.
Yes, sir.
Yeah, but that seems like a problem, right? Because then, if problem in many ways. First of all, the number of entries in Railtel's router will be huge, so search time will be huge. Okay. Second problem will be, if IIT Kharagpur connects a new machine, IIT Kharagpur has to inform Railtel every time, hey, I have connected this machine now. Okay. So that does not sound right. Okay. And the other thing is, for this entire bunch of machines in IIT Kharagpur, the next stop will be the same, which is basically going to be IIT Kharagpur's network. Okay. So IP routing is not done, this entry is not done by the host, it's done by network. So those destination addresses that you have seen in the routing table, for IP routing, the destination address will not specify a particular host IP address. It will specify a network in the either slash form or with the subnet mask. And then you will basically match to see, oh, this network, send it to the router for that network. The next stop will be the router address for that network, like this router here, the gateway here, and so on. And then that will pass it further. So we'll do that with the example starting tomorrow's class. Okay, we stop here. Tomorrow we need to go a little faster. We'll see what happens. Okay, so if there are any questions, I'm still here for a few minutes. Otherwise, class is over, so you can